And so we've gotten rid of the seasonal ups and downs. We have gotten rid of the kind of the main long-term trend, but we end up with some kind of some fairly, these fairly long period fluctuations that represent some kind of non-stationarity. Well, not sure what that represents. So in this case, the solution is to do both. To difference it once at 1 month lag, and difference it again at a 12-month lag, which now gives us a time series that doesn't have annual cycles, doesn't have this long-term trend, and also doesn't have this sort of intermediate term drifting up and down. So,
Bruce?
yeah.
So the first difference is just z minus 1.
Yep.
Which is on the top. And
Yeah.
this is
This is z of t minus z of t minus 12.
12. And then the last one?
And the last one, we do this, right? So we have z of t minus 1. That's our del of z. And then we do, basically we take del of z t minus del of z t minus 12.
Based on
The fact that we know that there's an annual.
Oh, I mean, but based on that difference between the bottom left.
Well, right. So this is the reason. Yeah. So if this just looked like a nice normal series without any and without these sort of drifting bits,
Then you're done.
then we could be done just with that seasonal difference. And it says that whatever this is probably summer, right? So summer travel this year only depends on summer travel last year, and there's nothing about what's going on in between, right? So the fact that we have processes, or we seem to have processes that depend both on the season and, well, some years just have higher travel than other years, right? And there may be that suggests that there's shorter term correlations going on as well. So the notation for our this is so the notation is so the notation for the annual differencing, or the 12-month differencing, is del 12 of dt. So that's the case that was on the lower left, and then the 1 month differencing, or the 1 time step differencing, is just del of dt. And so when you have them both, it's del 12. Right, so you do the 12 months differencing, and then you do a 1 month differencing of that. And these are actually, these are actually commutative. You can do it in either order and get the same result. Okay, so yeah.
How worried are we about the fact that last time series doesn't look quite stationary? Changes in variance.
This one, well, we might be worried about that. We can, yeah. So we're talking about this fact that the variance seems large here and smaller here and larger here. Yeah.
I guess at what point do you say, okay, it's stationary enough?
Yeah, well, I think, you end up getting to a point where there's nothing you can do that will make it more stationary.
Right.
And then you just have to, then what you're dealing with is that, this lack of variation sort of represents this period here where there's, very small month-to-month fluctuations in the seasonally adjusted travel.
If you knew something else about your process and you wanted to do a mixture of standard regression and time series, could you, just sort of thinking on the spot here, but could you throw in a regression coefficient that you knew was causing this non-stationarity to account for it first, and then look at the time series components?
Well, certainly you can, yeah, if you had a regressor, you could then do the time series analysis of the residuals.
Right.
But typically, actually, what you want to do is simultaneously, because the structure of residuals is going to cause bias in your estimate of that regression coefficient. So you actually want to estimate that altogether, and that's where you would use a generalized linear model, or not generalized least squares model, just as we did with spatial regression. It would say that it would model the residuals as having some autoregressive moving average structure. So here's just what the autocorrelation functions look like for those 4 time series, right? The one with the long-term trend, is just positively autocorrelated out to really long lags. The one where we did the first differencing, which still had the periodicity, you see really high autocorrelations at lag 12, at lag 24, at lag 36, right? That's the annual periodicity that you're picking out. The one that was just had the seasonal differencing had this pattern, which is associated with that drift, and then here is the autocorrelation for the one that's been differenced both ways, and we see a negative lag at 1 month, not much going on, a negative lag at 12 months, and then not much going on at subsequent multiples of 12 months. And so the argument that's made by the authors in the book is that the way you would analyze this is, this represents a moving average process, right? So an ACF that has just 1 lag is an MA process with 1 term, and then there's a separate MA process that was with the 1-year lag, but no subsequent terms. And I can't remember this. Yeah, and here's the PACF to show that it's hard to say what pattern is here, but you get a bit of a decay in PACF that suggests that this is more of a moving average process than a regressive process.
That's basically how these interpretations of these things go.
Yeah.
Sort of like to look at it and say,
Yeah, you look at it and say, well, what's my judgment on? So the seasonal ARIMA model, and then that'll be it for today. Let's see. So if W is that doubly differenced time series, so it's a result of that double differencing that I wrote down, and then there's 2 moving average coefficients. There's a moving average at lag 1 and the moving average at lag 12, the seasonal moving average. And so what we end up with is so WT, which is that difference time series, is going to be, there's a component which is the 1 month moving average, so theta 1 times A of t minus 1, and then minus, and a capital theta times basically then so what we're going to do with the 12-month moving average is take a moving average of this term and the equivalent term from 12 months ago. Okay, so it's A of t minus 12 minus theta times A of t minus 13. Okay, so the seasonal moving average is the moving average between, you know, this term and its equivalent a year ago. And the seasonal so the seasonal Riemann model is often written, so the Riemann model is just written Riemann P D Q. With the seasonal, we then cross that with P D Q in caps, and we note that it's a 12-month seasonality, right? And so in this case, it turned out that both the differencing and the moving average in the AR parameter, number of AR parameters, was the same in the seasonal and the short-term models, but they don't have to be the same, right? So you could have, maybe we didn't need a difference seasonally, in which case capital D would be 0, and maybe the seasonal pattern is an MA1 and the short-term pattern is an AR1. Okay, so you can have all kinds of combinations.
You have the same subscript on all of your thetas, but those are actually different thetas, right?
So these lowercase thetas are the same, and then this is a capital theta, which is different. This is the seasonal moving average parameter, and this is the this is the 1 month or the 1 month moving average. So again, you do throw all these manipulations of the time series to try and figure out how many differences are required to get stationarity and what the right number of lags is for the AR and MA processes, each of those. But then you just, in terms of actually estimating the model, you actually feed that into, feed those parameters, those numbers of parameters into the model that actually does the estimation and spits stuff out back on the original scale, which in this case is the log of passenger miles, which you can then use to make extrapolations into the future. So on Thursday we'll sort of go through this on the computer and